Hey everybody. We are going to develop a couple of nice properties. These have to do with symmetry of functions, using the substitution rule that make computing certain kinds of functions really, really easy. And it's pretty straightforward, and it is a very useful property. I know, for instance, that physicists use symmetry a lot, all different kinds, but this particular kind, you can often reduce a page or so of computations to a line or two by referencing symmetry. So let's talk about what I mean by that. So first of all, let's which one do I want to do first? Let's look at even functions. Okay. So an even function, it's a very simple definition, just means putting in a negative value and a positive value doesn't change anything. So x squared is the typical example. 2 squared is 4, negative 2 squared is also 4. And so it's an even function, right? So it doesn't matter if you put in the opposite of a number, you'll get the same number out, okay? So what does that mean for an integral? So if I have a function f that's even, and let's say I'm taking the integral from negative a to a, okay, so that part's important, that we're not just going over any interval, we're going over an interval that's symmetric about the origin, meaning it goes the same distance on both sides of the origin. Okay. Well, we can split this up into two integrals. Right, so my picture is just, right, whatever my graph looks like. If it goes from negative a to a, the first integral is this entire area. The sum of the two just means, well, let's do this area here and then do this area over here and add them together. And so it's very clear from the picture that those two things are going to be equal. It's one of the properties of the definite integral that we had. So let's take a look. We'll do a little work off to the side on this, this first integral here. So I'm going to come over to the side here and take a look at the integral negative a to 0 f of x dx. And I'm going to use substitution. I'm going to say that u is equal to negative x, which means that du is equal to negative dx, or negative du equals dx. Okay. Now let's go ahead and put those, make this substitution. So I have, instead of f of x, I'll have f of negative u, right? So that's just this substitution. F of x, since u is negative x, x is negative u, right? So I'm putting in place of u, I'm getting negative x. Okay, and then let's see, what else do we need to do? And then we've got du, but it comes with a negative. So I'm going to have a negative out front here. And let's change our bounds. When x is negative a, u is going to be positive a. And when x is 0, u is going to be 0. So with that substitution, here's our new bounds. Well, notice I have a negative out front and the integral from a to 0. One of the properties of the definite integral is that switching the bounds on the integral gives us a negative. So if I change this to 0 to a, I pick up a negative, but I already had a negative, it leaves it as a positive. Okay. At the same time, I'm going to use the definition of an even function. F is an even function. That was the entire basis of this whole thing. So f of negative u is the same as f of u, and du doesn't change. Okay. So that tells us, right? Now notice, this u is really just a change of notation. This is exactly the same as the integral of f of x dx from 0 to a, right? Because there's nothing special about u here after this substitution. So what does that mean? It means that I can rewrite this thing here as the integral from 0 to a of f of x dx plus 0 to a f of x dx, which is just 2 of this thing, right? I've got a thing and I add it to itself. It's 2 of that thing. So what is this telling me overall? That if I'm integrating over an even function on a symmetric interval, I could also do the interval from 0 to a and just double it, okay? Sometimes this is much easier, right? Because now we get to compute at 0, and sometimes that makes the whole computation a bit easier. And so graphically, this is a really easy thing to see. Let's use this. Whoops, that's not what I meant to do. 1 second. Let's use this. All right, so here's a pair of axes. An even function, right? One of the properties of an even function is that whatever it looks like on the right-hand side all right, pretend these look exactly the same. We get the mirror image of our function. And so what this is saying to us is if we were trying to find the area, let's make this negative a and this a. If we were trying to find the area here, 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 let's change colors. Let's make that side different, right? So our first integral, if we were going from negative a to a, would be all of this area, right? These two things. We can notice from the picture that the green area is the same as the blue, so it's just telling us you could also just figure out the green area and double it, okay? And sometimes that's a nice simplification. Probably even more useful is the following. I'm going to leave this one up to the viewer. Oops, not even function. What happens when we have an odd function? First, let's remind ourselves what an odd function is. It means if we put in a negative number, we get the opposite of the corresponding input value of the positive number. X cubed is our classic example. 2 cubed is 8, negative 2 cubed is negative 8, right? That's an odd function. Sine's an odd function. Cosine's an even function, right? So it's not just these powers, those are just good examples. So it turns out, through a very similar kind of process, which I will let you try, that if we have an integral of an odd function over, oops, this should be a to a, over a symmetric interval, so negative a to positive a, f of x dx, this is even simpler, it's going to be 0. Okay? This one's very easy to see with a picture. Do a picture here. So an odd function has the property, which comes straight from this definition, that if I look at what my function looks like on the right side, it's going to be exactly the same on the left side, but in the opposite direction. Right? So again, what we're imagining here is that I've taken this curve on the right side and rotated it 180 degrees, and you'll see it would line up more or less with the one on the left. And so if this is negative a to positive a, then the original integral is asking us to find all this area and this area and this area, and this area, right? But you'll notice that, for instance, this smaller green valley on the right is about, should be the same size, if this thing is truly symmetric, as it is going to be the same size as the small blue hill over here, except in the opposite direction. So one's negative, one's positive. they will cancel each other out. The same thing with the larger areas. And so we get this very simple computation. If you notice that something is an odd function, you don't have to do work to figure it out if it's over a symmetric interval. So it's proved in a very similar way, which you're welcome to give a try to. Let me just give a quick example. If I have something like the integral from -5 to 5 of, let's say x cubed minus 7x over the sine of x plus 2. No, that's not going to quite be an odd function. Sorry, that's not going to work. Let me do this easier. I'm overthinking this, which is a phrase that I do not like. There's no such thing as overthinking. Let's just do it this way. If I have x cubed minus x to the 7th plus x times the sine of x dx, well, oh wait, that's not going to be an odd function either. I need one more factor here. Let's do a factor of x. This is in fact an odd function, okay? And its integral is simply 0. Instead of having to go through all the work, I could simply show that it's an odd function by showing that this is true, which is easy enough to show. If I have, so f of x here is x times x cubed minus x to the 7th plus x times the sine of x. If I put in f of negative x, I get negative x. Negative x cubed is just negative x cubed, and I'll get plus x to the 7th minus x sine of negative x. All right, I've got a negative out here. Let's write it as a -1. I'm going to factor a negative out of the parentheses. So I'll factor out another -1. And then sine of negative x is equal to negative sine of x because it's odd. So I get another -1 from that factor. And what's left is x times x cubed minus x to the 7th plus x times sine of x. Well, these three -1s in the front just give me a negative x cubed minus x to the 7th plus x sine of x. But this is just negative f of x. All right, so that's an odd function, and this is 0. And even though this might be a little bit of work if you don't recognize this as odd, if you suspect it is, this is a small amount of work versus what you might have to do to take this integral otherwise, only to find out when you're done it was 0 all along. Okay, that's it for this one. Thanks, everybody. I will see you next time.